In this lesson, we are going to learn how to find the area between two curves. You already know that an integral, a definite integral, so say the definite integral from a to b of a function f of x dx is the signed area between x equals a and x equals b. And the area between two curves will be very much related to that. Okay, so suppose we have two curves, and they're continuous, and we are going to assume that f of x is greater than g of x on the interval from a to b. So let's draw a function f of x in red. So here's y equals f of x. Let's draw g of x in blue. Y equals g of x. And suppose that's a, and suppose that's b. So what we want to find is a way to figure out this area in between those two curves. Okay, call that area A. So if we find the integral from a to b of f of x, that tells us this entire area. And if we find the integral from a to b of g of x dx, that gives us that area. So the way to find a is to subtract those two. So in general, the area between two curves, assuming that f of x is bigger than g of x, the area is going to be the integral from a to b of f of x minus g of x dx. So the first curve is the upper curve, the second curve is the lower curve. This even works if one of your curves is negative. So look at this picture. So suppose that's f of x, and down here is g of x. And suppose you wanted to. Now, if you find f of x minus g of x, you will be taking away a negative number, which actually is going to make an addition, double negative. So in that case, even though g is negative, your area in this result is still going to be a positive number. So no matter what happens, when you find an area between two curves, you will always get a positive answer. In this case, this area is not signed. All right, let's do a few examples. So find the area of the region bounded above by x squared plus 2, below by y equals x, and on the sides by x equals 0 and x equals 1. All right, so let's graph x squared plus 2 in red. So x squared plus 2 is a parabola shifted up 2, so it goes to the point 0, 2, 1, 3, and 2, 6. So symmetric about the y-axis, so there's your parabola. Y equals x is a line with y-intercept 0, slope 1, starts at the origin. And we're looking for bounded on the sides by x equals 0, that's the y-axis. And x equals 1, that's this line right here. So the area we're looking at is that little region right there. And just based on counting the little boxes, it looks like it could be about 2. So my area will equal the integral from my left bound is 0, my right bound is 1. The upper curve is x squared plus 2 minus the lower curve is just x And now to find that area, you just evaluate this integral. So the antiderivative of x squared is 1/3 x cubed plus 2x minus 1/2 x squared. 0 to 1, so first plug in 1. So we'll have 1/3 plus 2 minus 1/2 minus 0. So that will be getting a common denominator, 2/6 plus 12, 6 minus 3, 6 is 11/6. And as we said earlier, that area is somewhere approximately 2, so since 11/6 is approximately 2, that sounds like a reasonable solution. Alright, so in that particular example, we were given the left and right bounds. And the next one will be a little bit different. So find the area of the region enclosed by the parabolas y equals x squared and y equals 2x minus x squared. So in this example, we were not told what the left and right bounds were. We must figure out where the curves intersect. So set the two expressions equal to one another. So x squared equals 2x minus x squared. So 0 is equal to 2x minus 2x squared. Factor out the greatest common factor of 2x. So these curves will intersect at x equals 0 and 1. Let's sketch their pictures. So y equals x squared is a standard parabola. It goes through 0, 0. Let's get one red. 0, 0, 1, 1, and 2, 4. And now 2x minus x squared, I think it's useful to factor that into x times 2 minus x. And then you can look at it and see that this is going to intersect the x-axis at x equals 0 and x equals 2. And if you plug in 1, you get that the value of this is 1. It's an upside-down parabola. So the region we're looking for, the area of, is that little bitty bit right there. Looks like the area is going to be something less than 1. And for our purposes, on that particular interval, so the bounds, leftmost bound is 0, rightmost bound is 1. That's not always the case. So for the part that we care about, the upper curve is the blue one. So we will have 2x minus x squared, and we'll take away x squared. So that's the area we're looking for we find by finding the value of this definite integral, 2x minus 2x squared dx. So the antiderivative is x squared minus 2/3 x cubed, evaluated from 0 to 1. So 1 minus 2/3 minus 0, and 1 minus 2/3 is 1/3. And once again, based on our picture and our estimation, 1/3 seems like probably a pretty reasonable area between those two curves. All right, so far that was pretty simple, so let's make it a little bit more complicated and consider some more complicated cases. So we assume that f and g are still continuous, but what if it isn't the case that f of x is always bigger than g of x? What if f of x is sometimes bigger, and what if f of x is sometimes less? So, for example, here's a picture. So here I have f of x, and here I have g of x, and I'd like to find the area between x equals a and x equals b. And let's call this little intersection point in the middle, we'll call that C. It's going to be useful later. So obviously you can't just do f of x minus g of x and integrate, because of the fact that from C to B the stuff flip-flops. But what you could do is just break this into two integrals. So your first portion from A to C. For that portion, f of x is on top. So we'll have f of x minus g of x dx plus, between C and B, well, on that portion, g of x is greater than f of x, so we'll have g of x minus f of x. And so if there is just one intersection point within the interval that you're finding the area between, then you'll just have two integrals. If there were two intersection points, you would have three integrals. So it gets very tedious very quickly, but that is, in principle, is how this is going to work. All right, here's an example of this. So we have the area between the curves y equals sine x, cosine x between x equals 0 and pi halves. You have to remember how to graph trig functions. Okay, so sine x first. So sine of 0 is 0. At pi halves, remember your unit circle here. At pi halves, the ordered pair there is 0, 1, so sine is 1. By pi, sine is back down to 0. 3 pi over 2, the sine is negative 1. And by 2 pi, we're back to 0. So here's my sine curve. Next, cosine. So cosine of 0 is 1. At pi halves, cosine is 0. By pi, cosine is negative 1. Then back up to 0, and back up to 1. And this intersection point is at x equals pi quarters. So we care about the area between these two curves between 0 and pi halves, so this portion plus this portion. So the area will be the integral from 0 to pi quarters. So for the up until pi quarters, cosine is first. Cosine is greater than sine. So we will have cosine x minus sine x dx. That gives us the area of the first region, plus the integral from pi quarters to pi halves. And for the second portion, we will have sine x minus cosine x. Now, technically, you could use some symmetry, and these two regions have equal area, and you could find the first integral and multiply by 2, but in principle, that isn't always true. It is for this particular example, but not everyone. So, all right. So for the first portion, the antiderivative of cosine is sine. And the antiderivative of sine, let's just see, cosine, that will have to be plus cosine of x. 0 to pi quarters. Plus, so sine's antiderivative is negative cosine x, and then minus sine x. From pi quarters to pi halves. So now first we're going to plug in pi quarters. Sine of pi quarters is root 2 over 2. Cosine of pi quarters is root 2 over 2. Then we plug in 0. Sine of 0 is 0. Cosine of 0 is 1. Okay, plus, next we plug in pi halves. So cosine of pi halves is 0, but sine of pi halves is 1. So we have 0 minus 1 minus, plug in pi quarters, negative root 2 over 2 minus root 2 over 2. So we end up with root 2 minus 1 plus root 2, or 2 root 2 minus 2. And as I said earlier, it would have worked just to find the value of this definite integral and multiply that by 2 because of the symmetry that we have here. So feel free to use those shortcuts if you see them. I think we're going to use that in the next one. Set up, but do not solve, an expression that gives the area between the curves 8 minus x squared, y equals x squared, and the vertical lines x equals 3 and x equals negative 3. So first let's figure out where these curves intersect. So 8 minus x squared equals x squared. So 8 will equal 2x squared. 4 is equal to x squared. So these curves intersect at x equals plus or minus 2. So the first function is a parabola shifted up 8 units. So we plug in 1, we get out 7. 2, we're getting out 4. Y equals x squared. Regular parabola. Now, the problem is we were also given the boundaries at x equals negative 3 and positive 3, and unfortunately, since these intersection points are at 2, well, unfortunately for us, that means we're looking at this kind of thing. And we need to find that area, all that area in the middle, and all that area on the end. Okay. Now here it's very useful, it's going to help a lot with the arithmetic to use some symmetry. So for the middle portion, to find the area between negative 2 and 2, so let's just set it up like this and we'll talk about how we can use evenness. Negative 2 to 2, the curve that is greater on that interval is the 8 minus x squared. Minus x squared. Now because this is an even function, and you can see this in the picture, one way to find this area is to do twice the area from 0 to 2 of 8 minus 2x squared. Now for those little tail ends. The tail end on the left has the same area as the tail end on the right. So we are going to do twice the integral from 2 to 3. And for that particular portion, the blue curve is above, so we'll have x squared minus the quantity 8 minus x squared. And be very careful you actually insert your parentheses there because that negative needs to distribute. So you take away the whole quantity. So plus twice the integral from 2 to 3. When we distribute the negative and combine like terms, we're going to get 2x squared minus 8 dx. Now, when you work out, let's just take out greatest common factor. So you can take out a greatest common factor of 2 in both integrals, making this 4. This is the integral from 0 to 2 of 4 minus x squared dx. Plus 4 times the integral from 2 to 3 of x squared minus 4 dx. When you work out all the details, you end up getting that this area is 92/3. In the online notes, I worked through the entire problem, so feel free to try to work this out yourself and check your answer and make sure that it's right. And if I'm wrong, let me know and I will fix it and give you extra credit. So now that we have done found the areas between some curves that intersect more than once, we're going to consider some examples where the world turns. So instead, what if you have curves, instead of having y as a function x, it's x as a function y. So what this is going to look like is this. So I have x equals f of y. and then x equals g of y. I'd like to find the values, the area of the curves between y equals c and y equals d. Now in this case you have to think about which way is up or which way is more positive. So drawing that arrow in for a reason. So since the positive numbers are in the direction of that arrow, f of y is greater than g of y, at least in the picture as I drew it. So to find this, the area between these curves, we'll find the integral. So we'll have f of y minus g of y, now dy, and then think lowest to highest. So here the lowest y value is c, the highest y value is d. So it's very much the same principle, it's just you have to think that up is to the right in the case. Let's give it. So find the area enclosed by the line y equals x minus 1 and the parabola, so actually sideways parabola, y squared equals 2x plus 6. So x minus 1, not super hard to graph. Go down 1, slope 1, rise 1, run 1. Let's actually graph that in red. The second one's a little bit more complicated, but I think the best way to do that is to solve this parabola for x. So we'll have y squared minus 6 equals 2x, or 1/2 y squared minus 3 equals x. And let's make a table of values. So we've got x, got y. So in this case, I'm going to pick y and find x. So if y is 0, x is -3. If y is, let's pick the numbers that work out nicely. If y is 2, 2 squared is 4, half of 4 is 2, 2 minus 3 is -1. So if x is, so back 1, up 2, and you can reflect that over the x-axis. This is just the parabola shifted backwards. Let's pick one more value for y. If y is 4, so 4 squared is 16, half of 16 is 8, 8 minus 3 is 5. So you go over 5, up 1, 2, 3, 4. It's lucky for us that that was the intersection point. You could also think about this as a stretched sideways parabola shifted backwards 3 units. To find the area between these curves, we'll find the integral from the lowest y value, so that first intersection point, that blue dot, the y value there is -2. The upper y value is 4. Now, our curves need to be expressed as functions of y, meaning you must have x equals something with y. So I have to take this curve line and translate it into x equals form. That's not very hard. X equals y plus 1. So we'll have y plus 1. Take away the lower curve we already have, x isolated, 1/2 y squared minus 3. So to find the area, find the integral from -2 to 2 to 4 of y plus 4 minus 1/2 y squared dy. The antiderivative of y is 1/2 y squared. 4's antiderivative will be 4y minus 1/6 y cubed. The arithmetic for these can get a little bit tedious. So first we'll insert 4. So we'll have 1/2 times 16 plus 16 minus 1/6 times 4 cubed is 64 minus 1/2 of 4 minus 8 plus 8/3. The reason that last one is plus, you plug in negative 8/6. Excuse me. Whew. 8/6. Okay, so that will be 8 plus 16 minus 32/3 minus 2 minus 8 plus 4/3. So that will be 30 minus 36/3, or 18. All right, let's do another one of those. So I have the curves x equals 1 minus y squared and x equals y squared minus 1. So it just helps to know that the standard sideways parabola x equals y squared looks like this. One way to think about that is, you guys all know what x equals root y looks like. That is just this. That's the root function. X equals y squared, technically speaking, to translate this into that, you need to have a plus or minus here. And the minus gives you the other half of that parabola. So let's do this one first. Y squared minus 1. So that takes the y squared and shifts it backwards 1. So backwards 1, and it has the same shape and structure as a general parabola. Now, 1 minus y squared, that negative in front of the y squared, flips this parabola about this guy, flips it over the y-axis, and then shifts it right 1. So that will look like this. So it looks like these curves intersect at y equals -1 and y equals +1, and we're looking for this area. And it looks like we can use some symmetry. So the area between those curves will be twice the integral from 0 to 1. Now the uppermost curve in this case is the red one, which is 1 minus y squared. Take away y squared minus 1 dy. So twice the integral from 0 to 1, 2 minus 2y squared dy. So that will be 2 times 2y minus 2/3 y cubed. So 2 times 2 minus 2/3. So 2 times 6/3 minus 2/3. So it'll be 4/3 times 2, or 8/3. So in summary, when you choose to integrate with respect to x or with respect to y, it's useful to think back to the definition of the integral as a limit of Riemann sums. So what I mean is this, is if you have your curves, and here's f of x, and here's g of x, and you divide this interval up into pieces, and you're finding areas of vertical boxes, and your width is delta x, you will use the integral from a to b f of x minus g of x dx. So this delta x parallels that dx. And if your curves are sideways, and we have x equals f of y, and x equals g of y, we would have made horizontal boxes. In that case, we would have a small change in y. And to find the area between, say, some c and some y value d, you'd integrate from c to d. And once again, because f of x is greater than f of y is greater than g of y, we would find f of y minus g of y. Now let's talk about what some of these things might mean in some kind of actual context. So this figure shows the velocity curves for two cars A and B. They start side by side and move along the same road. What does the area between the curves represent? So what does this area, we'll say up until 16, what does that area tell you? So first of all, the integral from 0 to 16 of a of t dt. So that's how far car A traveled, so the distance traveled by car A. And the integral from 0 to 16 of b of t dt is the distance traveled by car B. So there's car B's distance. Okay, so you have car A's distance minus car B's distance. So the area between the two curves tells you how much farther ahead car A is. So that's what this means. So the area between the curves is how much farther car A traveled. Or how far ahead car A is of car B. So that is what that means. And the last is a seemingly easy question. So let's first talk about what this question is asking. Find B such that the line y equals b divides the region bounded by the graphs of y equals 4 minus x squared and y equals 0 into two regions of equal area. So let's first sketch a picture of what we mean. So 4 minus x squared is a parabola shifted up 4. 1, 2, 3, 4. 1, 2, 1, 2. Okay, and now I want to find a line y equals some number b such that this area, the area below b and above b, bounded by that parabola, those two areas are equal. And you can kind of guess that that has to be somewhere between 1 and 2. So first of all, let's figure out what the total area underneath 4 minus x squared and y equals 0. So total area A will equal twice the integral from 0 to 2 of 4 minus x squared dx. And I'm going to spare you the boring details because you guys can differentiate and do arithmetic. You get 32 thirds for that total area. So the area underneath the parabola, bounded by the parabola and this axis, the x-axis is 32 thirds. All right, now to figure out where that line should be such that this curve is divided into two regions of equal area, it's actually easiest to think of stuff sideways. So I'm going to take this y equals 4 minus x squared, and I'm going to isolate the x. So y plus x squared will equal 4. X squared is equal to 4 minus y squared. Oops, 4 minus y. And so x is equal to plus or minus the square root 4 minus y. Now what I'm trying to solve, I need to find a b such that this area is equal to half of this. So the way that I would find that blue area is to integrate from, thinking sideways, my lowest, I'm slicing this way. My lowest y is 0. My uppermost y is b. And if I say have the integral of root 4 minus y dy, what that's going to just tell me is the area under that curve between the y-axis, so just that area. So to get the whole thing, I need to do times 2. And I need that expression to equal half of 32 thirds, or 16 thirds. And that's what we're going to try to solve. If you got that much, you're pretty much good to go. So divide by 2, half of 16 thirds is 8 thirds, so I have the integral from 0 to b, 4 minus y to the power of 1/2 will equal 8 thirds. Now it's not very hard to antidifferentiate 4 minus y to the 1/2. We'll have 4 minus y to the power of 3/2 times 2 thirds. And just think, if you differentiate this expression, you have 2 thirds times 3/2, which makes 1. Power of 1/2, the chain rule would give you times -1. You don't have a negative, so to compensate, you insert a negative out here. From 0 to b is equal to 8 thirds. Now what you can do to make stuff a little bit easier is you can multiply, before you even proceed, multiply both sides by -3/2. So we'll have 4 minus y to the 3/2 from 0 to b is equal to -4. Let's pick up where we left off, and we were solving in this integral the rest of the way. So first you plug in b. We'll have 4 minus b to the 3/2 minus 4 minus 0, so just 4 to the 3/2 equals -4. So 4 minus b to the 3/2. Okay, now 4 to the 3/2, first you root 4, which gives you 2, and then 2 cubed is 8, equals -4. So 4 minus b to the 3/2 will equal +4. And now it's just an exercise in Algebra 2. So first you will take both sides and square them, which gives you 4 minus b cubed is equal to 16. Next you will cube root. So 4 minus b will equal the cube root of 16. Take away 4, -b will be the cube root of 16 minus 4. Divide by -1, and b will equal 4 minus the cube root of 16. Technically that can simplify a little bit. 16 is 8 times 2, so b is equal to 4 minus the cube root 8 times 2, and 8 cubed roots to 2. So b is 4 minus 2 cube roots of 2. No one promised it would be a beautiful number. And there you have it. It's a seemingly simple question with a rather complicated solution. So that's all for areas between curves. Good luck with your homework.